Hello once again. Now we're going to the seminar. The first part is going to be more or less theoretical, while in the second one we're going to write our convolutional neural network ourselves in PyTorch. Let's start with reminding ourselves what convolution is, how it works. Nice animation shows you that we just slide a window through an image, perform element-wise product, and take its sum. Okay, as you can see, in 2D case, if we have image filter with size f by f, where f is kernel size, and we just do this thing, and in 3D case, our image would have, our input image at least, would have three channels, and our filter would also have three channels to match this thing. It's almost always true that the amount of channels in a filter matches the amount of channels in an input image. This thing is not true for MobileNet and some other derivatives, but you will not meet them very soon. Okay, stride is the size of a step the window takes, and kernel size is the size of the border of a kernel. Yeah, also I'd like to note that there is a convention of how images are encoded. Channels can go as the last dimension or the first dimension. In NumPy, in Matplotlib, it is usually considered that channels should go the last. And I think this is the most logical thing. Personally, I like this style more. But for PyTorch, channels should go as the first dimension for an image, since it allows to make some kind of improvements in computation, to make computations faster. That's the whole reason they do it like this. To remind yourselves how convolution works once more, you can go to this link. We will not do this since it was done in lecture. Okay, now we will write convolution with our own hands in pure Python. Okay. In your homework, you will have to do the same thing, but I hope that you will use NumPy, since this whole thing with NumPy, it makes a lot more sense. It is a lot easier, and if you're able to take this thing, this code, and rewrite it in NumPy, it means that you truly understand what happens. Also, while writing this code, I'm going to make some back references to NumPy functions, so that it would be easier for you to do the first task in your homework. First of all, we define a function called clip. What it does is it just takes in some number and clips it to be in the range from 0 to 255. Well, because images are encoded this way. Because after convolution, we can get the value which is above 255 or below 0, so we just clip them to be in that range. Also, we define a function called PSAMI. What it does is it takes a piece of image which has the same size as the convolutional filter. This is the convolutional filter. It performs element-wise product and then takes the sum. In NumPy, you would do something like this. a star b dot sum. This looks a lot better, and that's why I want you to do this thing in your homework in NumPy. Okay, let's load our image. We have downloaded it here. We use imread from image.io to do this thing. There is some bad things happening with image read from image.io, since for Windows and Linux the implementations are a bit different, and if we read JPG using this library in different places, it might be different for some pixels. The values of pixels might be a little bit different, and for this reason the whole homework should be done in Google Colab to make the results stable and reliable. Okay, here we read our image and take a small subset. Let's look at the whole image. I haven't done this. This is kind of classical image for image analysis. We take a small subset of this image because we are going to apply convolution, and in case of pure Python, in case of convolution written with our own hands, it would run like 10 minutes for the whole image, and we are not ready to wait this long. Okay, here we define our filters and perform the convolution itself. Actually, there is one more interesting note. In convolutions, we just do element-wise product and take the sum of these numbers. But here we are also dividing the results of our convolution by the sum of values in the filter. Why would we do this? Well, the reason is that, for example, imagine we have a filter filled with numbers 9. What it would do is most of the pixels, I think for an average image, would just turn to be above 255. We would clip them and the image would become simply a white square. And we don't want to perform convolution itself. Right now we want to kind of transform the image, to blur it, to increase the contrast, and to avoid such situations with the brightness being below, dropping below 0 or going beyond 255. We sum all the values in the kernel, in the filter, and kind of normalize the result so that it has approximately the same average brightness. Here we calculate this sum of values from the kernel. Oh yeah, and here we declare the metrics which will hold the results. We do it with NumPy because, well, we can plot NumPy matrices in a very convenient way. That's why we store it like that. Also, I'd like you to pay attention to this thing. We already know the convolution we are going to take is going to have 0 padding, well, no padding at all, and stride of 1. And with these variables, it's quite easy to calculate the size of an output. However, later in this seminar, we are going to introduce the full formula to calculate the dimensions of an output image, even when we have some padding, and stride is not equal to 1. Okay, what we do now? We want to slide our image, and the easiest thing we can do is kind of slide its top left corner. On most of the visualizations, the results of convolution of this element-wise multiplication and its sum is put in the center of where this window sits. But it doesn't really matter, and we can kind of use top left corner of that window as an anchor and slide this thing. Okay, what we do here is take pieces of image, just the size of our kernel, a red piece, green piece, and blue piece. Then we do element-wise multiplication and sum, divided by the sum of, this is the convolution itself, kind of. Then we divide it by div, which is the sum of numbers in kernel. It is not usually done in neural networks. Round it and clip. We do this for every channel separately. Even despite the fact that we have our input image with 3 input channels, we apply our 2D kernel to each channel separately, and thus this convolution is still 2D. We do this separately for every channel, and then assign the result to a pixel in our result image and show the result. Here it is, simply a blurred image. Okay, let's try something else. For example, let's try this filter and see what happens. It took some time, and now we have another image. Personally, to me, it looks quite the same. The reason is that these filters, they're not so different. So now let's take this one. I know that this filter should increase contrast, and I'm kind of intrigued to see what happens. Let's wait together this time. Yeah, you see this filter just increase contrast really much. And if we delete this division by div, what happens? No, nothing really bad. The reason is that the sum of the numbers in this filter is 1, and we simply divided by 1. Nothing changed. Let's take a look at a filter where it really means something. I think this one. If we apply it without dividing by the sum of numbers, we will get simply, white image, which is no desired effect. The reason we don't have to divide by div in neural networks, once again, is that in neural networks we don't clip our results, and all the operations happening inside of convolution itself are linear, and this division would do simply nothing. Okay, and if we return our div, it simply blurs. Okay. So now, as I have already promised, we're going to calculate the size of an output image after convolution. At first we have 50 by 50 image and 3 by 3 kernel with stride equaling 1. Calculating result is quite easy. It's just 50 minus 3 plus 1. How can you calculate this? Well, basically, when you try to slide the left top corner of the kernel, it cannot be in 2 last pixels, because then the kernel wouldn't fully fit into an image. And that's why we kind of minus 2 from the width of our image and get 48. The next example is when our image has 1024 by 768 size, and our kernel has size 5 by 5 and stride equals 2. Well, this example is kind of harder, and it isn't really frequent that you have to calculate these things with your own hands. So I think that it is useful to just write down the formula, check that it works on small examples in your head, like 7 pixels, 5 by 5 kernel and stride 2, something like this, and then apply it to anything else. The formula is the following. If the result is not an integer, then you should floor it down. Let's calculate the result for the width of the first image. We take 1024 minus the size of kernel, which is 5, plus 2 multiplied by the size of padding, which is 0, since it's not mentioned here, divided by stride, which is 2, and plus 1. We get 510.5. This is not an integer, and thus we floor it down to 510. However, if the result is not integer, it means that the convolution for your image is not symmetrical, that it doesn't treat every pixel kind of the same. For example, in the right here, some pixels on the right border would be just ignored. The convolution window would never slide over them. That's bad, and that's why you should design your kind of convolutional neural networks in such a way that this value is an integer. However, for big networks and big images, it's not that important. Well, for the height of this image and width and height of this image, you can carry out the calculations by yourself using this formula. It's not really a big deal. Okay, let's go further. We have learned some important concepts so far, which are convolution, what it is, how it is calculated, why it works, and questions like that. What is kernel, filter, what is stride, and padding. I hope that you already understand what all these words mean, and how you should, that you understand why are they necessary and how to change them. Because when we are going to get to actually building network, we will meet those words. Also, on the lecture, I said that we're going to talk about pooling a little bit more in the seminar. The time has come. There are many types of pooling. There are many operations which can be taken as pooling. On the lecture, we were talking about max pooling. Usually we slide the window in such a way that it doesn't overlap itself, such that the image is separated into pieces not overlapping pieces, where we take maximum and write it down as a result of max pooling. However, we can not only take maximum, but we can take minimum, we can take average, we can take sum, we can take product, and many other operations. But the most convenient is max pooling, when we take maximum from that windows, and average pooling, when we take the average value from that windows. What to use? Well, probably you would like to use max pooling as the first try. There isn't really much difference, and what shows itself better is dependent on the task. And yeah, there is a small note which just says that if we use max pooling with the size of our window equaling 2 and stride equaling 2, then effectively the size of our image will just be divided by 2. Okay, now we're going to the next part of our seminar, where we will write our own neural networks with PyTorch.